With the coherence conditions we covered earlier, we can document that as long as we select U and D of this form, with the binomial lattice, geometric Brownian motion, binomial lattice will be coherent. And so there's clearly a relationship between U, D, and the equivalent martingale measure probability. And so long as I maintain this relationship, it'll be an arbitrage-free lattice. If we solve for the multi-period binomial, you can check on the text to validate these results. But basically, we have an option value is going to be the present value, discounting at the risk-free rate, of the sum of the probability of a particular outcome times the particular outcome. Notice the use of the indicator function, so I can do both calls and puts with the same function if I'd like. And then also the probability raised to the j times 1 minus the probability raised to the n minus j. This is the likelihood of a single path arriving at some terminal value. And this is the number of paths that will get you there. And so this number is exploding high. This number is exploding towards 0. And so we need to be able to address that problem. So the multi-period binomial option valuation model can be written in this generic version where I can cover both calls and puts with the same function. The indicator function shows up in both in front of the first term, in front of the second term, excuse me, as well as the particular functional form of this of these summations. And these summations will eventually, in the limit, converge to the Black-Scholes-Merton ND1 and ND2 for the call, and N minus D1 and N minus D2 for the put. And so we know that we have this convergence property. And so this binomial model remains useful because we can address American-style options. The log transformation is very helpful because the number of paths explode, and then the probability of a single path tends to 0. And so given the way computers work and machine error, an extremely large number times an extremely small number is begging for machine error problems. And so if we take the log transformation, that basically converts this into the sum of the natural log of integers and then j times the natural log of the probabilities. And this resolves the problem quite nicely. And so American-style options, we again going to use backward recursion. We need to evaluate a host of different potential outcomes. The key is, from the American-style perspective, is we want to take the maximum possible value at every single node. And so the binomial model is again going to be the present value of the expected terminal payout. If I exercise it early, I can collect the moneyness of the option or the intrinsic value, and it also can't violate the lower bound. If the lower boundary is violated, then I'm going to capture the lower boundary amount. And so taking the maximum of these three values gives me the American-style option value. The digitals, I'm not going to spend a lot of time going through digitals. I would encourage you, it's a really nice way to think about exactly what a call and put options, what these things are. You can think of water as being hydrogen and oxygen. Well, a call option is comprised of an asset or nothing, a digital option, and a cash or nothing digital option. And so you can basically decompose these into parts, and their respective values are given here. Again, I don't want to get bogged down, but basically a call option on an asset or nothing, or an asset or nothing call option is equivalent to a plain vanilla call plus a cash or nothing digital call with the payout equal to the strike price. And so in this particular module, we introduced the multiplicative binomial model. We addressed how to deal with dividends, briefly introduced digital options. The beauty of the binomial model is it easily handles both European and American style options. We looked at a variety of plots generated in R, and now we're going to turn to the R code itself. We now turn to examining some of the R code that was provided with module 5.2. There's quite a bit of R code, and so I don't plan to go through all of it, but just introduce a few ideas, some of which we really didn't discuss in the book. And so if we just run through, this is the valuation. This is illustrating the valuation function of a European style geometric bounding and motion based binomial model. It's going to turn out that the functions are contained in this particular file, the European style GBM, BIN, OVM. And so if we take a quick look at the functions, we'll need a present value function. We're going to examine the lower bound. And then there's the upper bound, which really never comes into play. The binomial probability itself, again, using the log transform that we talked about, is a very efficient way to calculate this binomial probability. With the European style option, we're going to do both calls and puts using the same function, and indicator functions are keying on the type, and we're going to be able to compute both plain vanilla and digital calls, plain vanilla and digital puts. We only have to appraise the value at expiration. We don't have to use backward recursion. There is embedded in this code the sum of the probabilities, just to check to make sure that they sum to 1. There's a lot of different ways I could have handled this, but rather than return value, I could return sum just to check to make sure the sum of the probabilities equals to 1 as sort of an internal audit check. The American style option function is very similar. The only difference is we need to appraise early exercise, and in this case the lower bound is the maximum of either the European style lower bound or its intrinsic value. And so again, the upper bound is slightly different, but again, it's non-binding. And so to do American style, we basically have to have 2 loops. We have to have the backward recursion through time, and then we have to work backwards through each node. And at each node, we have to evaluate the moneyness and boundary conditions and do an appraisal at each node working backwards. Therefore, this particular function takes a lot longer to run. There's a lot of different ways to optimize this. You could consider building this module in C++, but that's a whole nother topic. And so let's look at how this could be actually used. For European style, we take out all the trash as we have before. We source the particular functions, which are here. And then we have a set of inputs. Now I used, running through these inputs, I used the dividend yield equal to the interest rate to be able to illustrate the influence of the implicit assumption of the log normal distribution. And the lower and upper bounds of the stock price are just for graphic purposes. And these graphs have a footer, and these footers have a set of values that I'm going to put underneath the graph to remind me of what parameters I was using for either digitals or plain vanillas. And we can basically test out the different models. In this particular case, the limiting argument with the Black-Scholes-Merton will be $11.34 or 35 cents, and so this appears to be functioning just fine. I'll do the same for puts. It's going to be the same value because the call equals the put when the dividend yield, equals the risk-free rate. Now, if I know that this particular program generates graphs, generates some plots, and so I'm going to make this a lot larger, come over here to plots. If I select the whole thing, I'm able to run it, and this will take a little while. Remember, this is backward recursion. This is European style, but it's still a binomial tree, and it has to run through a whole bunch of calculations for each option that is valued, and we're going to map across stock prices as well as across number of time steps, and so that's an enormous number of calculations. The only particular plot that I want to spend some time on is this European style option time value. Now, if you look at this carefully, you can see that there's the downward slopes are not symmetric. This one has more mass, which reflects the positive skewness of the log normal distribution. So if we wanted to contrast that with the idea of normalized values, we really don't have different stock prices at a point in time. We have different strike prices. And so if I rerun this model using the normalized version, then the question becomes, can I still see the log normal assumption when I'm looking at the strike price divided by the stock price? In this case, the stock price remains the same and the strike prices change. And so again, the answer is yes, we still see this positive skewness reflected. And this is going to turn out to be important because when we introduce the arithmetic Brownian motion version of the binomial model, that's the implicit underlying assumption is the normal distribution, and it's going to not have that feature. Now we could run the American style version. It would take too long for the time I have left. If I just reduce this to 50, it should run within the next minute or so. So using only 50 time steps, we can see clearly it's not as smooth as we would like it to be, but we get the features of American style, the fact that you would exercise early in light of the dividend yield for both calls and puts, and we basically see this in the graphs. And so the lower bound with American style is different than the lower bound with European style when there is dividends. And so I'd encourage you, if you have an interest in the binomial model, that you explore this particular code. There's several different files provided. There's the functions that are used for the European style binomial model where you don't have to use backward recursion. There's the American style where you do. It has an inner loop. It runs a lot slower. And then there's a variety of different test programs depending on whether or not you want to look at normalized results, that is strike price divided by stock price on the x-axis, or just vary the stock price itself. In the next module, module 5.3, we're going to explore a lesser known valuation of American style of arithmetic Brownian motion binomial option valuation model. Now, I happen to be a fan of the arithmetic Brownian motion approach, but that's not really the point here. The point here is you're an artist and you have the liberty to go out and create your own binomial model using whatever features you deem as most important.